Hi folks, we're going to take a look at the solution to page 158, number 21. Okay, so here we have an offshore oil well is located in the ocean 5 kilometers from the nearest point on the shore. Okay, so it's somewhere in the water, and it gives us the, perpendicular distance to the shoreline. Okay, and a pipeline is to be built to a refinery that is 20 kilometers along the straight shoreline from A. Okay, so it's a type of problem we've seen before. Now they do give us more information. They tell us that the cost per kilometer underwater is 100 grand and 75 grand to lay pipe online, and they want us to know the best route to take to get the cheapest cost. Okay, so similar problem to what we've seen before. Okay, so let's start by setting up our diagram here. So you've got your shoreline, okay, and somewhere out here you have your oil well, and they tell us that it's 5 kilometers from the shore, and they tell us that that's point A, and then we have to take it to the refinery, which is somewhere 20 kilometers downshore. Okay, so this is our scenario. So what we have to do is we have to minimize the cost. Okay, so how can this pipeline be built? Well, it could be built, it certainly has to be built at least part way underwater. Okay, so it's got to somehow come down to the shoreline. And unless you go all the way across to the refinery, part of it may be on land. Okay, so when I'm drawing my diagram, I always want to draw a general possibility here. So I'm going to draw this portion here along the water. I'll call that distance along the water, and I'll call this distance along land. Okay, so our cost, so again, what is it we're trying to optimize? We're trying to optimize our total cost, and so this is going to be $100,000 times however many kilometers we're going underwater, plus $75,000 times the number of kilometers that we're going on land. Okay, so this is what we have to optimize. As we've seen many times, two variables. Okay, so I've shown you this trick before if you've seen any of the other videos or in any of the other solutions. Okay, it's very easy to think, well, let's use DL as one of our variables, and that's just going to be 20 minus DL, which would be perfectly reasonable. The only problem is then when I use Pythagoras, which clearly I'm going to have to use to find an expression for dW, I'm going to have a square of 20 minus DL. Okay, which is going to make it a fairly complicated function. So what we choose to do instead is let's use this distance as a variable, which I'll call x. So it makes my Pythagorean expression easier, and DL, well, just becomes 20 minus x, which is a very easy function to deal with. Okay, so we have distance on land, 20 minus x, and our distance along the water, well, it's just going to be the square root of x squared plus 5 squared. Okay, and so now we have both of these variables in terms of the same variable, which is exactly what we want. Okay, so dW is square root of x squared plus 25, and then we have 75,000 times dl, which is just 20 minus x. And now we have a model in terms of one variable. Let's think about the constraints on this variable here. Well, if x is equal to 0, means we're going straight down to the shore and then all the way across 20 kilometers. So that is a possible solution. Or you can go straight across all along the water, in which case x is going to be extended all the way there. So at most, x can be equal to 20. Okay, so that's the constraint on our variable. So now we've got our model. Let us take the derivative. Okay, and so here 100,000 is just a constant, so no need to worry about that. So let's take the derivative of this thing here. So this is 1/2 x squared plus 25 to the negative 1/2 times the derivative of x squared plus 25, which is just 2x. Okay, we've done this many times before. 75,000, again, just a constant. And then here the derivative of 20 minus x, well, that's just a constant, so 0, and derivative of negative x is just negative 1. Okay, and of course we want to find the critical point, so we make that equal to 0. Okay, now I'm going to kind of skip a step here because I don't really need to keep this 100,000 and 25,000. So let's think about what their what their greatest common factor would be, and they're both divisible by 25,000. So since I have a 0 on this other side of the equation, I'm just going to divide both sides by 25,000. So I'm just left with 4 times, well here, let's cancel out the 2's. The only thing left in the numerator is the x, and this square root of x squared plus 25 just goes into the denominator. Okay, here minus, and 75,000 divided by 25,000 is 3. Okay, so it just makes life easier to simplify these things out. And so now bring the 3 to the other side. 3 is equal to 4x over this thing here. Let's multiply that to the other side. So 3 square root of x squared plus 25 equals 4x. And how are we going to deal with this? Well, I need to get rid of this square root, so I'm just going to square both sides. Okay, so this is where you got to be careful here, because remember, I'm squaring the whole left side. So don't forget that you're also squaring the 3. This just becomes x squared plus 25, nice and easy. And this becomes, again, don't forget to square the 4. This becomes 16x squared. So those are very common errors, forgetting to square the coefficients. So here we have 9x squared, which we'll bring to the other side. So 16 minus 9, so 7x squared. And so here we're left with 9 times 25. So 8 times 25 is 200, so this will be 225. Okay, so x, since it represents a length here, is just going to be the positive square root of 225 over 7. Okay, so we have to determine now what's going to give us the minimum cost. So let's first of all get a quick estimate here. So we have the square root of 225 divided by 7 gives us about 5.7. Okay, so how do we determine whether this is a minimum value indeed? Well, again, we've got a closed interval here, so I could test the value at 0, at 20, at 5.7. I just made a video on another question, which is what I did when we had a closed interval, but I think I'll just do it a little differently here. Okay, just to change it up, is I'm pretty sure this is going to be a minimum, especially since I've done a question like this before. So I'm just going to test that it is indeed an absolute minimum in the interval 0 to 20, which is all I care about. So 5.7, so I just need to test the derivative. Okay, so I'll use this as the derivative, simplified here. So I'll put in x equals, put in x equals 1. So what do we have here? So we have 4 times 1, so we have 4 divided by the square root of 1 plus 25 is 26. Okay, and then minus 3. And we've got something that is decreasing, and let's stick in, I don't know, x equals 10. So 4 times 10 is 40, divided by square root of 10 squared, so 100 plus 25, so 125. Okay, and then minus 3, and we've got positive. So here we know that in this interval, it's strictly decreasing this whole way down, and it's got to be strictly increasing that whole way there. So this ends up being an absolute min. Okay, so don't forget that last part of the process, which is to see exactly what they're asking. So it says, what route from the well to the refinery will be the cheapest? Okay, so we have to describe the route. So if we go back to our diagram here, okay, you're going to go on water to a point. Okay, so we found x was 5.7, so 5.7 kilometers from A, 5.7 kilometers from A, then the rest on land. Okay, and there you go, there you have it. So Let's just take a quick look at the final solution. So again, set it up as we've done many times before. Don't forget this trick. Try to pick a variable that's going to make your model as simple as possible. Okay, and don't forget this trick of scenario where you've got a square root on one side of an equation and then something that doesn't on the other side. You can just square both sides to get rid of that square root expression. Okay, that's it for this one.